Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 6. Extrapolation. Extrapolation refers to the process of estimating unknown values of a discrete function given at x0, xn, by extending the trends or patterns of the existing dataset beyond its original range of observations, that is, x less than x0 or x greater than xn. Extrapolation is used to predict future trends or values in fields like economics, weather, and population growth, to estimate behavior beyond the range of test data, such as in materials testing or structural analysis, to estimate unknown measurements from experimental data, and so on. The uncertainty in extrapolation is much greater, mainly due to the assumption that the existing trends will continue outside the data range. Linear extrapolation. The relationship between variables x and y is assumed to remain linear beyond the observed data. Exponential or logarithmic extrapolation. They are applied when the data follows an exponential or logarithmic trend. Polynomial extrapolation uses higher-order polynomials to fit the data and predict values outside its original range, allowing for more complex curves than linear extrapolation. In this method, it is important to choose the right degree based on the behavior of the dataset, ensuring that the extrapolated results are reasonable and reliable. Newton's divided difference method is a suitable technique for extrapolation, particularly when dealing with non-uniformly spaced datasets. To extrapolate uniformly spaced datasets, the Gregory-Newton Forward or Backward interpolation formulas, see Video 3, providing an incremental way to build the polynomial, can be applied. The choice of formula depends on the position of x in relation to the data range. In some cases, polynomials fitted using the least squares regression can provide a solution for extrapolation, and cubic splines can be advantageous for extrapolation when the dataset is smooth and stable, and the realistic model is described by a quadratic or cubic polynomial extrapolation. To extrapolate for values of x less than x0, the Gregory-Newton Forward interpolation formula with the first row, x equals x0, as the baseline is used. Because x0 has the most entries in the difference table as shown in the figure. Here, the interpolation variable s is defined as x minus x0 divided by h. To extrapolate for x values greater than xn, the Gregory-Newton backward interpolation formula with the last row, x equals xn, as the baseline is used. Because of the fact that the row xn has the most entries in the difference table as shown in the illustration. Here, the interpolation variable s is defined as x minus xn divided by h. The farther you extrapolate from the known data, the more uncertain your predictions become. Always validate models and avoid extrapolating too far beyond available data without additional evidence supporting the continued trend. In order to obtain a reasonable estimate, the discrete function should be smooth and suitable for a polynomial extrapolation. In this respect, the backward or forward interpolation tables offer a clue as to how good an extrapolation may turn out to be. For smooth functions, the magnitudes of successive higher-order differences along the chosen baseline should decrease. In part of the figure, the magnitudes of the increasing differences along the heighted baseline decrease, which implies that a fourth-order extrapolating polynomial will give a converged estimate. In part B of the figure, the magnitudes of the increasing differences along the heighted baseline increase after the first difference, which implies that a second or higher degree extrapolation polynomial will tend to diverge from the true solution. In part C of the figure, the magnitudes of the higher differences increase after the second difference, which implies that a third or higher degree extrapolation polynomial will tend to diverge from the true solution. A univariate extrapolation is the simplest way of data estimation. An extrapolation method allows estimating the quantities that are not directly measurable or observable, or that are too costly or CPU time intensive. Polynomial extrapolation can model a wide variety of data patterns, including linear, quadratic, cubic, and higher degree relationships. It helps fill in the gaps outside the data range, making the data more complete and consistent. The handicaps of extrapolation methods are: the quality of the extrapolation depends on the assumptions made and/or approximations that may not always hold true or represent the reality of the data. The extrapolation process is significantly affected by the fluctuations in the existing datasets. Extrapolation can introduce errors and uncertainties in the estimated values, especially when the data is noisy or extrapolated far beyond the original data range. Consider the following discrete dataset. Use polynomial the extrapolation to estimate f(0) and f(4.5). The true function is given as follows. We note that the dataset is uniformly spaced with h equals 0.5. Since we are seeking f(0), we will use the Gregory-Newton Forward interpolation formula for the extrapolation purpose. We adopt the first row, the row x equals 1, as the baseline, and we evaluate the interpolation variable s to be -2. It is observed that as the degree of differences increases, their magnitudes along the baseline decrease. However, just to be safe, we will not blindly sum up all the terms in the forward difference formula. The sum of the first two terms results in the linear extrapolation. The sum of the first extrapolated value with the third term of the interpolation formula leads to quadratic extrapolation, and the sum of the second extrapolated value with the fourth term yields the cubic extrapolation. Since the last fourth-degree difference is 0, we cannot improve the extrapolation any further. Meanwhile, notice that, as we increase the polynomial estimation, the magnitude of each new term added has decreased. The extrapolated value with the cubic polynomial turns out to be the true value. Next, we will be estimating f(4.5), which is a value further down the row x equals 3. So we use the Gregory-Newton backward interpolation formula in this case, using the row x equals 3 as the baseline. The interpolation variable s becomes 3. Notice that as the degree of differences increases, their magnitudes also decrease. This can be viewed as the sign that the higher-order polynomial extrapolation will converge to a more accurate result. Yet, just like before, we will not blindly sum up all the terms in the formula. The sum of the first two terms is the linear extrapolation, which yields 568. The sum of the first extrapolated value with the third term is the quadratic extrapolation, which results in 760. The sum of the second extrapolated value with the fourth term is the cubic extrapolation, which results in 820. Meanwhile, as we increase the polynomial estimation, the magnitude of the new terms added has decreased. The extrapolated value for x equals before using the cubic polynomial also turns out to be the true value, which is not surprising since the true function is a cubic polynomial. On this note, we conclude this video. That is all for now. See you next time with another topic. Bye.